So let's verify that x equals pi over 4 is a critical point of the function f of x equals sine x plus cosine x, and then determine whether it is a local min, local max, or neither. So first of all, let's find the derivative of the function. The derivative of sine x plus cosine x is cosine x minus sine x. So instead of it finding the critical points, I've just given you one and asked you to verify it. So here this is going to be f prime of pi over 4 is cosine pi over 4 minus sine pi over 4. That equals root 2 over 2 minus root 2 over 2, which is 0. So the derivative at pi over 4 is in fact 0, so yes, this is critical. So x equals pi over 4 is a critical point. All right, so now we want to determine, is it a local min or a local max or neither? Now we know that we could use the first derivative test. We could do an analysis of whether the first derivative is positive or negative on the intervals to the left and right of that point. But sometimes the second derivative test is easier to use because all we have to do is sometimes evaluate a very simple derivative, a very simple second derivative, and then evaluate it at just one point. So here, f double prime of x, since we see what f prime of x is cosine x minus sine of x, f double prime of x is going to be negative sine x minus cosine x. So that means that f double prime of pi over 4 is equal to negative root 2 over 2 minus root 2 over 2, which equals negative root 2. Now, we don't really care about the fact that it's negative root 2. What we do care about is the fact that it's negative, because that's what the second derivative test requires. We're simply using the fact that that this function is concave down at pi over 4 to say that it is therefore sitting at the top of a concave down function, so it's kind of at the top of the mountain instead of the bottom. And what that means is that we can conclude that since f prime prime of pi over 4 is negative, therefore, call it those three dots like that means therefore, x equals pi over 4 is the location of a local max. And we don't have to do an analysis on the intervals to the left and right of that point, because it's just enough to just to evaluate the second derivative at that point. So so there's one example. So here's a different problem where we're asked to find and classify the critical points of f of x equals x to the 5/3. So all right, first let's find the critical point or points. We know that we find the first derivative. So f prime of x is going to be 5/3 x to the 2/3. We can see that this function is defined everywhere, and it's going to be 0 only where x equals 0. So we can see that x equals 0 is the only critical point. I'm not going to put up the process of solving this expression for 0, because I think that as you listen to me, hopefully you can understand why x equals 0 is the only solution to this expression, to where this expression is equal to 0. So let's try to classify this point using the second derivative test. So let's find f double prime of x. And that's going to be 2/3 times 5/3 times x to the, subtract 1 from 2/3, and I get negative 1/3. So that equals 10/3 x to the negative 1/3, which is 10 over 3 times the cube root of x. So as we can see, we have x in the denominator. If I plug in 0, I'm just going to get division by 0, and we know that that's not allowed. So here we have a situation where we were actually able to find that 0 is a critical number by setting the derivative equal to 0, and yet we don't have a defined second derivative, so we can't apply the second derivative test. Therefore, we have to go back to the first derivative test. That's the only thing you can do. So we can go back to the first derivative test. And what that requires us to do is ask whether the first derivative changes from positive to negative or vice versa across the critical number. One of the things that's nice about the fact that we have only one critical number, 0, is since the function, the second derivative we know is not going to cross through zero. Sorry, the first derivative is not going to cross through zero any place else except at zero, because that's the only critical number. If the first derivative could be zero someplace else, then that would be a critical number. That means that I can just pick any number to the left and right of the critical number and ask whether the first derivative is positive or negative there. And that will stand in these points here that I've chosen, negative 1 and 1, which I've chosen because they're convenient to evaluate. They will stand in for the sign, SIGN, of f prime for the entire interval negative infinity to 0 and 0 to infinity. So let's evaluate f prime of negative 1. So that's going to be 5/3 times, this is going to be the cube root of negative 1 squared. Well, negative 1 squared is just 1, its cube root is 1, so that's just going to be 5/3, and f prime of 1 is equal to 5/3 times the cube root of 1 squared, which is obviously just 5/3 again. So we see that the first derivative, f prime, not f1, f prime, we see that it's positive to the left of the critical number, and it's also positive to the right. So there's no sign change, and what that tells us is that x equals 0 is neither min nor max. So the point of this example is that even though it turns out that x equals 0 is neither a min or a max, the second derivative test was inconclusive. I got no conclusion from it. I can't just say, oh, well, it was 0, so therefore it was neither a min nor a max, and I knew that from the second derivative test. You didn't. The only thing you knew from the second derivative test was that we didn't know anything, and we had to go back to another test to find out the answer. Let's go on to yet another example. This is kind of an interesting pathological case that I like to put up. Let's find and classify the critical points of f of x equals x to the fourth. So see that f prime of x is equal to 4x cubed. So once again, x equals 0 is the critical point, and it's the only one, because clearly this is defined everywhere, and the only place where 4x cubed is 0 is at 0. Now look what happens when I try to find the second derivative and apply the second derivative test. This is going to be 12x squared. So if I evaluate f double prime of 0, I get 12 times 0 squared, which is just 0. Well, what happens when you get 0 in the second derivative? It means the second derivative test is inconclusive. So once again, we don't know whether we don't know whether x equals 0 is a min or a max. So let's go back to first derivative test. Isn't this great? I show you this great test. It's really easy to use. Then I give you two examples where it doesn't work. Well, that's the point. It's a really nice test where it works, but sometimes it doesn't, and sometimes you just have to go back to the first derivative test. So here, what we're going to do is we're going to ask what is the value of the first derivative at two arbitrary points to the left and right of the critical point. So that's critical, and we just pick two arbitrary points to its left and right. So that's and by the way, if there were more than one critical point, like let's say there was a critical point out here, let's say that there was C2 like that, you could certainly pick a point to the right of 0, but it would have to not cross over the next critical point. Fortunately, we don't have that in this case. We just have we only have a single critical point, so I can pick any point to the left and any point to the right. So anyway, f prime of negative 1 is equal to 4 times negative 1 cubed, which is negative 4. F prime of 1 is equal to 4 times 1 cubed, which is 4. So what we see is that the first derivative is negative to the left and positive to the right. So we conclude, therefore, that the function is heading down, down, down on the left and then up on the right, and we conclude that x equals 0 is the location of a min. But we were only able to determine that through the first derivative test. Now let me just show you what's going on with the graph of f of x equals x to the fourth. In this graph, what this graph looks like really is like this. And some people say, oh, it's just a parabola, because Frankly, many students coming out of pre-calc assume that parabola is kind of a synonym for a function that looks like a u. It's not. Parabola specifically refers to the graph of a quadratic function. There are plenty of other u-shaped functions that are not parabolas, and this is one of them. The technical term for a fourth degree function is quartic. So quadratic is a second degree function. Quartic is the name for a fourth degree function. In any event, what's going on here is that this point is a point where the function flattens out so much that the function just has no concavity. So this function is concave up, concave up, concave up, concave up, and then it flattens out and has nothing right there. And then it goes back to being concave up again. So there's this one point where the function is so flat that it has no concavity, and that's why we're not, even though this is clearly sitting at the bottom of a bowl, mathematically we're not able to detect it through its second derivative because the function flattens out. So it's not even the case that functions that are bowl-like even necessarily have detectable concavity at their top or bottom. This is just a pathological case that I like to put up to demonstrate that point.